see if this actually works. Okay. So number 1 covers our first objective, which is to use the kinematic equations in conjunction with Newton's second law. So here's what those look like. Newton's second law is this, and the kinematic equations are those equations from last chapter. They look like this. Vf equals Vo plus At. Vf squared equals V initial squared plus 2A delta P. And the other equation that will be useful with Newton's second law is this one. Delta P equals V initial T plus 1/2 AT squared. I'll provide these equations for you on the test, but I think you should be able to recognize that these are called the kinematic equations, and this is called Newton's second law. Let's apply it to the problem at hand, which is, with an initial speed of 21.7 meters per second, a driver activates the brakes of a car such that it skids to a stop over an 18-meter distance. Calculate the net force acting on the 900-kilogram vehicle. I'm going to write down everything they gave us here. They said calculate net force, so I'm going to remember that by writing sigma F equals question mark. They say from the top here, an initial speed of 21.7, so that's VO. A driver activates the brakes such that it skids to a stop. What does that imply? If something comes to rest like this, which of our values is 0? Very good. Someone answered privately here. VF is 0. We also have it skids to a stop over this distance right here. Technically, distance and displacement are different numbers. In our class, they always end up being the same thing, so we don't need to differentiate between distance and displacement. They've also given us later on, let's see, calculate net force acting on right there. I know this is mass because it's in kilograms. So although I won't ask you to put units on your answers in the test, it's useful to know what the units are because they help you figure out what they represent. Knowing that mass is in kilograms allowed me to put it right here. And that's all that was given. If we go to find net force here in this equation, if we go to calculate it, I would plug in 900 right there, and I would find that acceleration is not known. And that's where the kinematic equations come in. We can find the equation that has all three of these and acceleration. And with that, we'll be able to find the acceleration. I can't use this one to find acceleration because although I have VF and VO, I don't have T. Same story down here on the bottom one. I can't use this to get acceleration because I don't have a number to plug in for T, so we'll use this one. Every problem's a little different though. On the test you might be using the top or bottom one, but we'll use this to get acceleration. Here we go. Sigma F. Oh wait, no. What am I doing? That equation there. I'm not going to rewrite it. I'll just plug the numbers straight in. So it's 0 squared equals VO, which is 21.7. 21.7 plus 2 times A times 18. You can rearrange the numbers first and then type in your calculator, or you can type in your calculator every step of the way. I'm going to do it that way. So this will be 0 equals 471 plus 2 times 18 will be 36A. So now I'll subtract 471 on both sides. That leaves us with negative 471 equals 36A, and then we divide both sides by 36. So that's our acceleration. The question is actually asking us for net force. So if I want to calculate my net force, I take the acceleration I just found and I multiply it by the mass. So that's the point of Newton's second law. It says that the net force acting on an object is the mass of that object times the acceleration of that object. So sigma F is going to be 11790 newtons. So this is the net force being used to slow the car down. Actually, it's negative. Okay. If you have questions about that, let me know now. If you're still looking, let me know. Okay. We'll go on to number 2. Number 2 is all about Newton's third law. And what we do here is we kind of use the definition of Newton's third law to answer some questions. So here's the third law. For every force, there is an equal and opposite force. All that stuff about for every action there's an equal opposite reaction, throw that out. Don't worry. Don't think of it that way. Think of it in terms of force. When you say action and reaction, it sounds like you're talking about motion. It sounds like you're talking about acceleration, but that's not what it is. It's all about forces. So in these pictures up here, we see 3 cases of that. And I want you to be able to name the forces. I think it's pretty easy to do. For example, this one here would be bat pushes ball, ball pushes bat. Here would be ball pushes pin, pin pushes ball. And here we have a bus that's hitting a bug. Bus pushes bug, and even though it doesn't seem like it, the bug is also pushing the bus. I think this is a good example because it's an extreme case. So this is the one we'll write down, but I think the other 2 are pretty similar. So I'll do A, B, and C for the bug and the bus. It says, write down the name of the action-reaction pairs, and that's what I just did. It's like this. Bug pushes bus, and in order to get the other force, you just swap the nouns. You always have noun, verb, noun. You'll swap those. So bus pushes bug. And that's how you write action-reaction pairs. Each of these is a force. The bug pushes the bus pushes the bug, and part B is my trick question about those 2 forces. I wonder if anyone knows it. Answer to my trick question, it is, which object experiences more force? Take a guess in the chat there, or shout it out. I'm trying to trick you, so don't feel bad if you get it wrong. Both wrong so far, I'm sorry. Take a look at the law. There you go. You could say both or neither or same or equal. The point is the forces are the same. Neither force is larger than the other. The thing that differs is their acceleration, which is what C asks us. Which one accelerates more? It's the bug. Why does the bug accelerate more? Because it has less mass. So this is 4 logical steps that I think are quite easy if you remember this. You just have to remember that the forces are equal. With the baseball bat, in red here, I'll put the answers to the baseball bat. You don't have to write them down. Bat. It would be same thing. With the baseball bat, which one accelerates more? The ball accelerates more. Why? Because it's less mass. That's the point. The forces are equal, but the accelerations are different. And the accelerations are different because of the masses being different. It has nothing to do with force in this case. Spoiler alert, this is the one that'll be on the test. The one about the bus and the bug. Because it's so counterintuitive. You'd expect the bus to push with more force, but not really. The reason the bus doesn't slow down when it hits a bug is because it's just so massive. It has a lot of momentum. A lot of inertia. All right, let's keep flying here. Number 3 puts Newton's third law into Lansing. Which one do y'all call him? Okay, number 3, what am I saying? Number 3 puts this concept into math terms. We're just using Newton's third law to solve problems. So the equation is written in the problem there. It says use this equation. But you have to know when to use it. We'll see why this is the correct equation pretty quickly if we go to label everything. Consider a bowling ball that strikes a single pin. The 5.4 kilogram bowling ball. Okay, let's write that mass down. Mass is 5.4. I'm going to keep writing all the numbers they give us. It experiences an acceleration of negative 0.667 meters per second squared. And the pin experiences an acceleration of 3.34. Calculate the mass of the pin. So M is our question mark. Look what we have here. M equals 5.4 kilograms. A equals negative 0.667 meters per second squared. Another A is 3.34, and another mass is supposed to be calculated. So since there's 2 M's and 2 A's, it should be quite obvious that the equation with 2 M's and 2 A's is relevant here. The only trick is you got to keep your information isolated. Since this is about the bowling ball, they'll go together as number 1. And since this is about the bowling pin, they'll go together as number 2. So we'll plug them in. 5.4 times negative 0.667 equals negative M2 times 3.34. There are two ways to solve here, two methods. You can multiply these two together and you can rewrite the equation, at which point you'll divide both sides by this, or you can just start by dividing both sides by that. So up to you and how you want to solve this one. I'm going to save myself some time. I'm going to divide both sides by negative 3.34. So the negative cancels the negative. The 3.34 cancels the 3.34. And here I have a nice, beautiful term that I can just type into my calculator all at once. 5.4 times this number divided by this number. And it looks like the negatives canceled there too. M2 is 1.08 kilograms. All right. So there's our third law equation. Number 4. Let's see how I want to do this. The rest of the problems are all about gravity. Yeah, let's just keep flying. Number 4. Mars has a mass of 6.37 times 10 to the 23rd kilograms and a radius of 3.39 times 10 to the 6th meters. Calculate the acceleration due to gravity on Mars. Acceleration due to gravity is lowercase g, and it only appears in two equations. It appears in this one, which is the definition of little g. It also appears in this equation, but it doesn't really work here. We don't have like an object to reference. If they told us like this is the weight, this is called weight or gravitational force, that is not given in this problem. All they give us is mass and radius. So I hope this equation jumps out at you for little g. Mass and radius also appear in this equation. So you might think that since mass and radius are given, you'd use this, but no, this is for gravitational force. So once again, we don't have Fg. So let's do the calculation. The capital G is always this number. (6.67 times 10 to the negative 11th). That's the value of capital G. M depends on the planet that you're talking about. In this case, it's Mars with a mass of 6.39 times 10 to the 23rd. And the radius of Mars is 3.39 times 10 to the 6th squared. So plugging in the numbers is quite easy in my opinion. The challenging thing is to type it into your calculator. So I recommend you practice it at least once, whether that be now or later. If you're having calculator issues, I can help you at the end of class, or I can help you during office hours. Yeah, and remember, this is just G. This is capital G. It's always that number. Why is capital G this number? No one knows. If I had an answer for you, I'd also have a Nobel Prize, which I don't see coming my way anytime soon. So it's just a fact of the universe. So 3.71. Number 5. Number 5 asks us for gravitational force. So we'll actually use that third equation. 5 is the gravitational force between a student and her cell phone. So planets and stars aren't the only things with gravity. They're just large enough for us to see and observe the gravity. Everything in this universe that has mass also has a gravitational field, a gravitational force associated with it. It's just that when these things are too small, we can't tell that it's actually there. So number 5 is about a person standing near their cell phone, and although you feel the need to walk over to your cell phone all the time, it's not actually gravity. That gravitational force is too small. So we'll calculate the gravitational force between this person and their cell phone. Didn't even actually read it. So the student has a 0.056 kilogram cell phone. It's 1.25 meters away from her, and her mass is 60. Calculate Fg between her and her phone. So once again, I don't have much to say about plugging the numbers in. I think the challenging thing here is properly using your calculator. This one is, I'll make sure, there we go. So this one will be very small, 1.43 times 10 to the negative 10th newtons. Very important to have this scientific notation term. It's 1.43 times 10 to the negative 10. That means that it's a very small amount. Really, this decimal place is 10 places that way. So basically, there's no force. I mean, it's almost no force. It's technically there, but we just can't feel it. It's such a small amount because this person and her phone are too low mass. Here's something that you might do. Well, yeah, basically all I want to say here is this equation, this is for the amount of gravity that a planet is pulling you with. So we could calculate the gravity on the phone and the person, but we wanted the gravity between them, and that's why we used this. So let's do that for 6 and 7. 6 and 7 are super easy. Really all I'm doing for 6 and 7 is testing that you know the difference between mass and weight. This is weight, also known as gravitational force. Ooh, I forgot my I in there. Weight, aka grav force. Weight, also known as gravitational force, and this is mass. Don't mix those two up. So number six says calculate the mass of a 450 Newton object. They're describing the weight. 450 newtons, they're saying it like they say pounds. Calculate the mass of a 450 pound object. Same thing here. We're just using newtons as the unit for weight. So it's 450 equals m times 9.8. This one is, it's the opposite on number 7. They say calculate weight given this mass. So Fg is 70 times 9.8. And I hope you know how to do that algebra. .9 and 686 newtons. And that is all she wrote. If you follow it along just fine, please post that on Google Classrooms. Be ready for that test tomorrow. If any questions come up later, shoot me an email. I've got office hours 2 p.m. today and 8 a.m. tomorrow. Just email me before those times. If you want to meet at 2 p.m., let me know before. Otherwise, I'm not even going to open the office hour meeting. If you want to meet tomorrow morning, let me know by 7:30 a.m. and I'll open it up for you. Otherwise, I assume you got it. So if you have questions or you want to see something again, stick around. Otherwise, you're free to go. Have a great day, and I'll see you tomorrow.